This is an old goods lift installed in 1955. This video goes through how the logic circuits work, with all the attention to detail that you can expect from one of my videos. I hope not to disappoint. In part 1, we watched this lift in action. Cameras were placed everywhere and synchronized together to bring you lots of different views. The lift was installed back in 1955 by a company called J&E Hall from Dartford in Kent, UK. In this part, we delve into the controller cabinet and how the relay circuits work using this old-fashioned schematic on the front here. All this footage from part 1 and part 2 was not filmed by me, so out of respect for all the work that went into filming, I'm going to quickly mention the United Lift channel. There is some really unique footage, including an old Hammond and Champness lift. This mechanical floor selector demonstrated using LEDs, and the lift in the 8th floor building it came out of, also installed in the 1950s or 60s. Please give the United Lift channel a visit. Links to these videos are in the video description and can also be clicked at the end of the video. Now back to this video. First of all, let's have a quick run through all the components on the schematic, which represent everything in the motor room. At the top are circuit breakers that cut the supply to the lift if an overload is detected. Here it is. These are called dashpots. When overloaded, the oil inside them heats up, which trips the unit. Here are the relay contacts. This symbol here represents a normally open contact, and this one is for normally closed. Normally open breaks a circuit. Normally closed allows a circuit to flow. When a relay is powered, both contacts go active. Now, the normally open contact makes a circuit, and the normally closed now breaks a circuit. When the relay turns off, the contacts return back to their normal state. Personally, I'm more used to these symbols instead. Normally open makes a circuit. Normally closed breaks a circuit. By the way, these large relays are actually called contactors and are designed for high current circuits. Most relays in the cabinet have several contacts. For example, the up relay is powered here, and the contacts are drawn all over the diagram. Here are the relay contacts. The ones at the top switch the high currents to the motor, whereas the ones at the bottom are for the logic circuits. These represent the two windings inside the motor. One winding makes the motor go fast, and the other one makes it go slow. I'm coming back to this choke later on. The bridge rectifier converts the incoming main supply from AC to a DC voltage to run the relays and timers of the logic circuits. It looks like the original one was replaced, and I'm not quite sure if this one hanging around in the back of the rack runs the whole cabinet or not. Now the relays. Brake release. Fast. Slow. Choke. Time delay. R1 controls the fast and slow speeds. TA is another time delay relay, and then the motor up-down relays. Here are the call buttons. These buttons are inside the lift car, and these ones are on the landings. The call buttons are wired in parallel and activate the same circuit from either location. These symbols are the roller switches attached to the lift car. They are activated by ramps on the lift shaft wall as the lift moves up and down into them. To see them in action with my multi-camera views, please see my previous video. These roller switches are for the slowdown and these are for stop. There's another one at the top of the diagram for over travel. This one is a little mysterious, as I will explain later. Last of all, these are resistors, which I'll also explain later on. Let's get going. First of all, let's see the sequences in action on the lift in real time. Here is the idle state. Assuming all gates are shut, no stop buttons are pushed, power travels to the bridge rectifier, and voltage is now available to the logic circuits. Every circuit is blocked by a normally open contact. These are from the up and down relays and the call buttons. If the lift was on the lowest floor and you press the down button, this contact prevents anything from happening. It's the down roller switch, which is currently pressed by the lift. It blocks the path to activate the down relay when the lift is already at the lowest floor. A passenger now enters the lift car. Opening either the inner or the outer doors cuts the power to the bridge rectifier, which in turn removes power to the logic circuits and relays. If you open the inner doors whilst the lift was moving, this would stop the lift moving immediately, and you'd have to reselect your destination after the doors were shut. We push the first floor call button. On the outside of the lift, there is an up-down button. This means you can send the lift to its destination without needing to be inside. The next sequences actually happen within about half a second. The up call button creates a circuit to the up relay, which now energizes. All the associated up contacts now go active. Normally open contacts make a circuit. Normally closed contacts now break a circuit. There's a normally closed contact here just before the down relay, so that when up is active, the circuit to the down relay becomes broken, which prevents both up and down relays being powered at the same time, at least electronically. In addition, both up and down relays cannot physically be on at the same time, because there is a physical linkage between them. With the up relay active, this blocks the down relay via this pin shown here. And it's the same for the down relay, which blocks the up relay. Here is a demonstration of the physical interlock between the up-down relays. Before we continue, nothing is guarded in these old lift cabinets, meaning you can easily touch live connections. Doing so could expose your body to 415 volts, which could quite easily lead to your death. Never touch anything in lift cabinets. This lift is currently turned off for maintenance, and the guy in this video has already checked that no power is entering the cabinet. If it were to be possible for both up and down relays to activate at the same time, this would cause a short circuit between two of the phases, and it would probably blow the contacts apart before it tripped the circuit breaker. Another of the up contacts creates this path, which is part of the up self-latching circuit. This allows the up call button to be released without the up relay turning off. Therefore, whilst this relay is on, it maintains the power to the up relay. Now let's have a look through the logic circuits, remembering that all this happens within half a second. If either up or down relay is energized, the logic circuits become powered. The brake is applied at all times. When it's powered, this releases the brake to allow the motor to spin. There is a switch within the brake mechanism when it releases, and it changes the path of the circuit through this resistor. The resistor reduces the current slightly, so the initial brake release was powered in full, then the resistor is introduced to prevent the brake solenoid becoming too hot during operation. I'm going to jump to the R1 relay. This is powered by either up or down relays. The R1 relay remains active until the slowdown roller switches are pushed later on. Here are the normally open and normally closed contacts for the R1 relay. With R1 now active, the normally open contacts join to allow current to pass to the fast relay. The normally closed contacts now break the circuit to the slow relay. With the brake released and the fast speed selected, now let's have a look at what's already happened at the top high voltage section that runs the motor. The direction is up, and the fast relay is active, allowing the three-phase main supply to reach the motor's fast windings, and the lift starts moving. If the direction was down, then the red and yellow phases will be swapped over like this. The AC sine wave now feeds into the motor the other way around, causing the motor to go in the other direction. The path to the slow windings are blocked here, because the slow relay is not active yet. Now the TDL relay, which means time delay. The TDL relay switches on. It's priming the introduction of the choke for operation a little later. For now, this part of the process is just to charge up this capacitor. I'm coming back to this later. With the TDL relay on, this also breaks the circuit a second time to the choke. Either the up or down relay activates the TA relay, which is another timer. When the up relay turns off later on, this capacitor will keep the TA relay energized a little longer, creating a time delay. In reality, all that I've just described happens this quickly. The motor now drives the lift at high speed. Well, it's not really that quick, but you have to compare this with the slow speed, which is, well, slower. The next sequence is when the lift reaches the slowdown roller switch. The roller switch cuts the circuit to the R1 relay, which turns off, and its associated contacts return back to their normal state. This means the fast relay is turned off, and the slow relay is now turned on. Now creates a circuit towards the slow speed windings of the lift motor. But first of all, we need to eliminate any spikes or surges in the supply, which could originate momentarily back from the high speed windings. This is the job of the choke, which is currently engaged. With the slow speed relay on, this now cuts the supply to the TDL timer relay. But with the capacitor still with charge, the relay does not turn off immediately like the others. This delays the introduction of the choke bypass relay via these contacts. When the capacitor loses all of its charge, TDL then turns off. but we're only talking about half a second or so, enough time for the choke to do its job, completing the circuit to the choke relay, and it energizes. The choke relay has 3 contacts. Each of the contacts now places a short circuit over the choke for each phase to give maximum power to the slow speed motor windings. By this time, the choke has already done its job and is now bypassed and disengaged. It could be that the capacitor that runs the TDL relay is faulty, as there doesn't seem to be any delay here at all, or it's so slight it's hardly noticeable. With the lift now running at slow speed, the next sequence is the stop roller switch. When it's pushed, this breaks the circuit to the up relay and it turns off. The self-latching circuit is then removed, and everything connected to an up relay contact is also switched off, and also the TA relay supply is removed. But with this being connected to a capacitor, the TA relay stays on for a little bit longer. So what's the function of the TA relay? With this still energized, this cuts the circuit to the call buttons for a short time. This allows the passenger inside the lift time to open the lift doors before someone else can call it back in the other direction. After a few seconds, the capacitor discharges, and the TA relay then turns off, by which time, hopefully the passenger has already opened the doors. As before, opening the doors to exit the lift cuts the supply to the bridge rectifier, preventing anything from happening until the doors are all shut. And we seem to have an addition at the bottom here. Whenever the gates are shut and the logic circuits are powered, this LKR relay activates. If someone leaves the gates open and a call is made on the other landing, this runs a bell to attract someone's attention to shut the gates. There's a couple of bells on this lift. There's one on top and one underneath the lift car. I'm not entirely sure which is the lift alarm bell, but I'm guessing the one underneath is the gate open bell. Whenever the logic circuits are active, LKR relay is powered. This activates a normally closed switch, breaking the circuit to the gate open bell. When a gate is open, the LKR relay is down powered. The normally closed contacts allow power to the gate open bell circuit. But the circuit to the bell is not complete yet. It's completed by pressing any of the landing call buttons. There is one part of this diagram that I've not yet mentioned. This circuit incorporates the final roller switch, which is for overtravel. If the stop roller fails for whatever reason, the overtravel roller is pushed by the ramp beyond the top and bottom floors. Now, I would have expected this to be part of the circuit that breaks the supply to the bridge rectifier. Instead, this NV device is activated at all times and is switched off when the lift overtravels. NV could be a relay, but I could not find any contacts for it anywhere on this diagram. So NV must somehow shut down the lift, but as I said before, I don't know why the NV device is needed in the first place. It might be that when NV is activated by the lift overtraveling, perhaps this NV has to be manually reset by an engineer before the lift will run again. If you know what this NV device is and how it shuts down the lift when the lift overtravels, please let me know in the comments. All in all, I hope you agree, everything is very simple, but it's all very interesting. And I hope that I've done this old lift justice in my video. Thanks once again to the United Lift channel for the footage shown in this video. To see a hand-picked video from me from the United Lift channel, please click the video in the top right. And if you've not seen part 1, you can see it by clicking the video in the top left. The Mr. Matt and Mr. J channel goes above and beyond to bring you quality, well-edited videos. Now, this is just a request and not a demand. Liking the video really supports us, and even better, we never say no to a new subscriber. If you think we've done a good job here, please consider subscribing, and thank you very much for watching.